There is a method that costs less than $4, takes under 10 minutes, and can add over 100,000 miles to any car engine. It requires no special tools, no mechanical training, and no appointment at a shop. It has been documented in engineering journals, tested by military fleets, and used quietly by long-haul truckers for over 70 years. And yet, if you walk into any dealership today and ask about it, the service advisor will look at you like you just asked them to put out their own fire. They will not tell you. Because if you knew this, you would never need them again. This is the story of the engine trick that the automotive industry buried. Not because it failed, because it worked too well. Let me take you back to where this all started. The year is 1942. The United States military is running a logistics operation unlike anything the world has ever seen. Thousands of vehicles, jeeps, trucks, armored transports are being pushed across deserts, jungles, and frozen tundra. Supply chains are stretched to the breaking point. There are no dealerships in the Sahara. There are no service centers in the Pacific jungle. If an engine failed, men died. So military engineers were given one directive: make these engines last as long as physically possible using whatever is available. One of those engineers was a man named John Muir. Not the naturalist, a different John Muir, a mechanical engineer working out of a depot in North Africa. Muir noticed something that the official maintenance manuals never addressed. Engines that were treated with a specific combination of common mineral compounds before long operations showed dramatically less wear on cylinder walls and piston rings. The compound was not exotic. It was not classified. It was a mixture of fine graphite powder and a small amount of castor oil, two substances that had been sitting in storage crates since before the war. Muir documented his findings in a field report filed in 1944. The report showed that engines treated with this compound before high-stress operations showed up to 40% less cylinder wear after 50,000 miles compared to untreated engines running the same routes on the same fuel. The military took note. Fleet maintenance protocols were quietly updated. The compound became standard practice in long-haul military transport for the next 2 decades. Then the war ended. The soldiers came home, and the automotive industry began building something far more profitable than long-lasting engines. But before we get to that, let me show you why this actually works. Because the science is not complicated. It is just something they stopped teaching. Every internal combustion engine operates on the same fundamental principle. Pistons move up and down inside metal cylinders thousands of times per minute. The surfaces of those pistons and cylinders are never perfectly smooth. Even machined metal has microscopic peaks and valleys called asperities. When those surfaces grind against each other at high speed, those peaks shear off. That is engine wear. That is what slowly destroys every engine ever built. Motor oil reduces this friction, but oil has a limitation. Under extreme pressure and the kind generated at the moment of combustion, the oil film between metal surfaces can collapse. This is called boundary lubrication failure, and it is the single most destructive event that happens inside your engine on a daily basis. Every cold start, every hard acceleration, every moment of high load. The oil film thins, the metal touches metal, and microscopic damage accumulates. This is where graphite changes everything. Graphite is a form of carbon with a layered molecular structure. Those layers slide against each other with almost zero friction, a property called lamellar slip. When fine graphite particles are suspended in oil and circulated through an engine, they deposit into the microscopic valleys of metal surfaces, filling the asperities and creating a solid lubricating layer that does not collapse under pressure. Unlike oil, graphite does not thin out under heat. It does not evaporate. It does not oxidize. It bonds to the metal surface and stays there. A study published in the journal Tribology International in 2009 measured the friction coefficient of steel surfaces treated with graphite oil suspensions versus untreated surfaces under boundary lubrication conditions. The treated surfaces showed a 60% reduction in friction coefficient and a 73% reduction in surface wear rate. These are not marginal improvements. These are transformational numbers, and graphite is not alone. Castor oil, the other component in Muir's original compound, has a molecular structure that bonds directly to metal surfaces through a process called polar adhesion. Unlike petroleum-based oils, castor oil molecules carry a slight electrical charge that causes them to cling to metal even when the oil film is under pressure. This is why castor oil was the lubricant of choice for aircraft engines in World War I. It was not tradition, it was chemistry. The combination of graphite's solid lubrication and castor oil's polar adhesion creates what engineers call a sacrificial boundary layer, a coating on the metal surface that absorbs friction and wear so the metal itself does not have to. The engine runs cooler, the cylinder walls last longer. The piston rings maintain their seal further into the engine's life, and the result is an engine that simply does not wear out at the rate the manufacturer's warranty assumes it will. Now here is where the story takes a turn. In the 1950s, as American car culture exploded and the automotive industry became one of the most powerful economic forces in the country, a quiet but deliberate shift happened in how engines were designed and maintained. Engineers at the major manufacturers understood the concept of planned obsolescence, the idea that products should be designed to fail within a predictable time frame, driving repeat purchases. This was not a conspiracy theory. It was openly discussed in industry publications. Alfred Sloan of General Motors wrote about it directly in his management philosophy. An engine that lasts 300,000 miles does not sell a new car. An engine that lasts 120,000 miles does. The math is simple. The incentive is clear. Maintenance manuals were rewritten. The graphite castor compound disappeared from official service recommendations. Dealership training programs focused on oil changes, filter replacements, and scheduled component swaps, all of which generate recurring revenue. The concept of treating the metal surfaces themselves, of building a protective layer that extended engine life beyond the warranty period, was quietly removed from the conversation. Not banned, not debunked, just forgotten. And the trucking industry noticed. Long-haul operators who could not afford to replace engines every 150,000 miles kept using the old methods. Fleet mechanics passed the knowledge down through informal channels. Shop talk, handwritten notes, the kind of information that never makes it into a YouTube algorithm. For 70 years, the people who depended most on engine longevity kept this knowledge alive in the margins. While the mainstream automotive world sold you a new car every decade. Here's what you need. Fine graphite powder, available at any hardware store or online for under $3 per ounce. Food-grade or pharmaceutical-grade castor oil, available at any pharmacy for under $5 per bottle. That is your entire material list. The process is straightforward. Mix 1 teaspoon of fine graphite powder with 2 tablespoons of castor oil. Stir until fully suspended. Add this mixture directly to your engine oil through the oil filler cap. Do this at your next oil change when the oil is fresh. Run the engine for 15 minutes at idle to allow the compound to circulate and deposit onto cylinder walls and bearing surfaces. That is the entire procedure. For best results, repeat this treatment every third oil change. The graphite layer builds up over time, filling surface imperfections progressively. Engines treated consistently from early in their life show the most dramatic results. But even engines with high mileage benefit from reduced friction and lower operating temperatures. A mechanic in rural Montana has been treating his personal vehicles with this compound for over 20 years. His 1998 pickup truck has 340,000 miles on the original engine. His 2004 SUV crossed 280,000 miles last spring without a single internal engine repair. He is not a legend. He is just someone who never forgot what the industry tried to make him forget. The cost of this treatment over the life of a vehicle, under $50 total. The cost of a replacement engine, between $4,000 and $8,000. The cost of a new vehicle, $30,000 to $60,000. The automotive industry generates over $2 trillion in annual revenue. A significant portion of that revenue depends on engines wearing out, on warranties expiring, on repair bills accumulating, on the moment you decide the old car is not worth fixing and walk into a showroom. A $4 treatment that doubles engine life is not just inconvenient for that industry. It is an existential threat to the replacement cycle that the entire business model is built on. Some knowledge does not disappear. It retreats. It waits in the notebooks of fleet mechanics and the memories of engineers who learned from men who kept these engines running across deserts and jungles when there was no other option. The engine in your car right now is wearing down. Every cold start, every hard mile, every moment of boundary lubrication failure is taking something from it that it will never get back. Or you can give it back. $4, 10 minutes, 100,000 miles. The industry forgot to tell you. Now you know.